Another example of an optimization problem, we are going to find the point on the line y equals 2x plus 3 that is closest to the origin. So first, a picture. The line y equals 2x plus 3 is a line with slope 2, y-intercept up here at positive 3. So this line will look approximately like this. We're interested in finding the point that's on this line that is closest to the origin. Closest to the origin is probably going to be, somewhere right around in here. So as we're working on the problem, I expect that we will get x to be negative and y to be positive, but that's no bother to us. So first question is, how do we identify that this is an optimization problem? What hints do you see in the wording of the problem? Big things to look for would be words like maximize, minimize, or some sort of superlative. This one has a superlative, something that ends with est. Closest means that we are going to minimize the distance. So in terms of defining variables here, there's really only two variables that need to be defined, and they are going to be that ordered pair that we see on the line. This will be an ordered pair on the line. Now with that in mind, we also need to define, according to the distance formula, what is the distance between this point and the origin. So the distance between the ordered pair xy and the ordered pair 0, 0, applying the distance formula, I'm actually going to use L for a length of this line segment is going to be the square root of x minus 0 squared plus y minus 0 squared. Again, that is the distance formula. And simplifying what this expression would be, that would be x squared plus y squared. Now, that gives us our objective function. We are trying to minimize L. Our objective variable is now L. But that gives us L in terms of two variables. We need to find some sort of relationship between x and y that's going to allow us to make a substitution, and here is that relationship between x and y right there. Y is equal to 2x plus 3. So we're going to perform that substitution on the y variable. This will be x squared plus 2x plus 3 quantity squared. Now, I think that some expanding and combining of like terms is in order. So first thing I'm going to do is expand the 2x plus 3 quantity squared using my second favorite four-letter F word, which is FOIL. Combining like terms is going to give us 5x squared plus 12x plus 9. That'll give us length in terms of only one variable. Now, with that in mind, generally what we look for is an associated domain for x. However, if we take a look at the original line extends infinitely in both directions, so there really isn't going to be any sort of domain issue with this. Also, upon inspection, when you have a square plus a square, there's no value that I can plug in that will create a negative under the radical, so we don't need to worry about the domain associated with the radical. Now, a step of algebra in anticipation of what we're about to do. We are about to take a square root, take a derivative, and the thing that we like to do with square roots is express them as 1/2 powers so that we can apply the power rule to what we have. So, flipping over to the other side of the page, I'm going to recopy down what the objective function is. This is L is equal to 5x squared plus 12x plus 9 raised to the 1/2 power. We are now ready to take a derivative. That derivative is going to be dl over dx, and that'll be equal to 1/2 times, this is applying the power rule, 5x squared plus 12x plus 9 raised to the negative 1/2 power. Then the chain rule says also multiply by the derivative of the thing that was being raised to the 1/2 power. That'll be 10x plus 12. rewriting this using a little bit of algebra, the 10x plus 12, 10x plus 12 can go in the numerator, and the denominator is going to be 2 times the square root of 5x squared plus 12x plus 9. I guess we could take it one step further and actually apply the 2 to the two things in the numerator and call that 5x plus 6 over the square root of 5x squared plus 12x plus 9. Now, for us to find critical values, we'll need to set this equal to 0 and solve for x. We've already pointed out, though, that there's no situation in which this denominator could possibly be equal to 0, so the only way that we're going to get critical numbers out of this fraction is if the numerator is equal to 0, which gives us a considerably nicer looking equation for us to try to solve. In fact, 2 quick steps of algebra will get us to an answer, and we get that x is equal to negative 6 over 5. Now, as a reminder, though, the original problem said determine the point on the line that is closest to the origin. If we know the value of x, we'll need to calculate the value of y. The substitution that we had for y is that y is equal to 2x plus 3. So that'll be 2 times negative 6/5 plus 3. That'll be negative 12/5 plus 15/5 for an answer of 3/5. Now, when we started this process, I did point out I do anticipate the value of x to be negative and the value of y to be positive. I'm going to go ahead and flip back to our original graph and say, does it make sense that this guy right here would be about negative 6/5 and 3/5? I would say so. Now, another quick calculation lets us know that hopefully this problem makes sense. In order to figure out the closest point on here, we would need to go in a perpendicular sense. The slope of this line here happens to be equal to 2. The slope of this little line segment that we have right here, if you perform a calculation on the change in y and the change in x, that would be 3/5 divided by negative 6/5. And if you simplify that fraction, you get negative 1/2. Negative 1/2 is the opposite reciprocal of this 2. So hopefully it makes sense that these two lines would have to be perpendicular to each other, and that is the result that we got. So hooray and huzzah and celebrations all around.